Our universe is built from just over 100 different fundamental building blocks, the elements. From the stars in the sky to the cells in your body, these elements are the alphabet of the cosmos, and deep within each atom lies the essence of its very nature, the nucleus. Today, we will uncover the secrets of that small, dense heart of the atom and enter the world of isotopes. At the heart of every atom is a nucleus, a tiny, dense structure packed with positively charged protons and neutral neutrons. The number of protons defines the element. If it has 6 protons, well, that's carbon. 17, that's chlorine. Looking at the periodic table, we see that each element has its atomic or proton number displayed next to its symbol. And this is indeed the number of protons, which is fixed for every element. But what if I told you that not all atoms of an element are exactly the same? That the nucleus, although consistent in charge, can vary subtly with its mass. You see, although the proton number is consistent, the number of neutrons can vary, and we call these variations in nuclear structure isotopes. A UK examiner might ask you to give a definition of an isotope, and I would suggest that you remember this one. An atom with the same number of protons, but a different number of neutrons. Isotopes isn't a word we hear very often, but you may have heard this word in a cartoon. In The Simpsons, Springfield's baseball team is called the Isotopes, and that's linked to their local nuclear power plant. I'm stood in front of Hartlepool's nuclear power station. That's it in the background, over there. Power stations such as this do indeed run based upon the decay of radioactive isotopes of the element uranium. And the temptation here is to link all isotopes with radioactivity, but that is simply not true. Every element in the periodic table has isotopes. Some are stable, some undergo nuclear decay, some are common, and some are rare. But there is one simple fact: you are surrounded by isotopes. There's even a hint at their presence if you look at the copy of the periodic table given out to pretty much every GCSE student in the UK. Look at chlorine's entry. Chlorine has a relative mass listed of 35.5 units, which, given that chlorine has 17 protons in its nucleus, would mean that it had 18.5 neutrons. And it's just not possible to have half a neutron. Something must be going on here. In fact, there is a big simplification in the periodic table, which we've overlooked so far. These masses are not what they appear to be. They're actually averages, and they have to be because of the existence of isotopes. You see, 3 out of every 4 chlorine atoms have 18 neutrons in the nucleus, and the other quarter, well, they have 20. Scientists need a way to talk about these isotopes and distinguish one from the other. So what we do is we follow the name of the element with its mass number. So we have chlorine-35, where we have 17 protons and 18 neutrons, and chlorine-37, which has 17 protons and 20 neutrons. When we average those masses, we get 35.5. Now, a UK examiner might ask you to use the data on an element to calculate the average atomic mass. So let's have a quick look at how we do that calculation now. Here are chlorines 2 naturally occurring isotopes, chlorine-35 and chlorine-37. The examiner would give us what is called the abundance of each isotope, and that is just the percentage of that isotope in samples of the element. If you recall, I said that 1 in 4 atoms of chlorine were chlorine-37, and so its abundance is 25%. The remainder are chlorine-35, and so chlorine-35's abundance is 75%. To construct a weighted average, we must multiply the mass of the isotope by the abundance of that isotope, and then we add the results together and divide the total by 100. If we put the numbers for chlorine in, that will give us 2,625 plus 925. If we add those together, we get 3,550, and when we divide that by 100, we get 35.5, the average chlorine relative atomic mass, which is the one listed in the periodic table. There's a worksheet on my Patreon page, as usual, with another couple of examples on there for you to have a go at. And if you'd like some support with those, I've worked through those in some YouTube shorts, which I've linked below in the description, so you can just click on those if you need the help. But what I'd like to do now is mention another common isotope. This here is a lump of sea coal that's just washed up on the beach down there. And just like you and me, this lump of coal is packed full of carbon atoms. We've talked about carbon several times already in this series of videos, with its 6 protons and 6 neutrons. But that's not the full story. In fact, 1% of carbon, and that's the carbon in you, me, and this bit of coal, isn't carbon-12 at all. It's carbon-13. And of course, carbon-13 atoms have 6 protons, but 7 neutrons in their nucleus. Now, this difference makes absolutely no impact whatsoever on their chemical properties. In fact, in terms of their chemical reactions, it's impossible to tell isotopes of any element apart from their lighter or heavier brothers and sisters. But when we work out the average mass of a carbon atom, which I've done on the worksheet as another example, what you'll see is that it's not exactly 12. That 1% of carbon-13 makes a difference. There is one more isotope of carbon we should mention, and that is carbon-14, which has 8 neutrons in its nucleus. This is again a naturally occurring isotope, but it's much rarer than carbon-13. In fact, only 1 in a trillion carbon atoms are carbon-14, and they are not stable. They undergo nuclear decay and turn into atoms of nitrogen-14 in a process known as beta decay. This means that all life on Earth is actually slightly radioactive. Now, that's nothing to worry about, but it is the secret behind something we call carbon dating. And that's the process that scientists use to date everything from ancient Egyptian mummies to long-lost English kings. Interestingly, carbon also gives us one more thing. It gives us the standard by which all other masses are measured. When we say relative atomic mass, you might well ask, well, relative to what? The answer is, it's relative to 1/12 of the mass of a carbon-12 atom. And this gives us another definition that you should commit to memory for your GCSE studies. Relative atomic mass, which is the weighted average mass of the naturally occurring isotopes of that element, taking into account the abundance of those isotopes and measured relative to 1/12 of the mass of an atom of carbon-12. The periodic table you use at GCSE has most masses rounded to the nearest whole number, but in fact, very few of them are true integers. You can start to see this in the version of the periodic table used at A-level, where the first decimal place is shown. However, remember that each isotope of every element must have a whole number of neutrons in its nucleus. So the mass number of an isotope will always be a whole number. And so, what have we learned about isotopes? Well, you know that isotopes are atoms of the same element with different numbers of neutrons. That isotopes of each element are chemically indistinguishable from their isotopic partners, and that only a few of them are radioactive. So, remember that isotopes are everywhere, in the air we breathe, the food we eat, and in fact the very fabric of our bodies. They are a quiet reminder that even the simplest things in nature are rarely quite as simple as they seem. I'll see you next time.